You guys saw yesterday that there are two kinds of lenses. Lenses are a great application of refraction because they bend light in a specific way to produce specific, predictable images. The two types of lenses were convex and concave. This is a convex lens. It's thicker in the middle than it is at the edge. But there's also another name for this lens, this convex lens. What's the other name for a convex lens, one that's thicker in the middle than it is at the edges? Gareth, there's your hand up there? No, it doesn't. You're thinking of the other one, but you're on the right track. It's converging, yes. This is a converging lens, and the reason that we call it a converging lens is because rays of light converge. Rays of light that go through this lens come together. Now, I would prefer that you use the terms converging and diverging rather than convex and concave. Over the next couple of days, it's going to become even more important that you use those terms. So what I'm going to suggest that you do, if you ever see the word convex on a quiz or a test, translate it in your mind to converging lens. The reason that those terms converging and diverging, in my opinion, work better is because they describe what's happening to the light. Rays of light don't convex. Rays of light converge as they go through this lens. Now, there's a few things that we want to label on this ray diagram that we see here before we actually draw the ray diagram. First one is going to be this line right here that goes straight through the center of this lens. What are you going to call this line right here? This imaginary line that goes through the center of the lens. Yep, we're going to call it the principal axis. Principal axis goes straight through, perpendicular to the lens and through this geometric center of the lens. Now that geometric center of the lens right here is called the optical center. Yeah, it's called the optical center of this lens. Now this point right here, this is a point where all rays that are parallel to the principal axis will converge. Or in other words, all rays will focus at this point. What are you going to call that point where all rays focus? The focal point. Not all rays, I shouldn't have said that. All rays that are parallel to the principal axis will focus at that point. This point right here is the focal point. This one we're going to call 2f. That's just a little spacer, meaning that the distance from the lens is twice the distance as it was to the focal point. And on the left-hand side, we don't really have, if our object is on the left-hand side, we don't really have a focal length on this side, but we're going to call it f just as a spacer, and 2f, again, just as a spacer. But I put quotation marks around it because you know that there's not really any optical significance of those points on the left-hand side, the same side as the object, just as spacers, that's all. Okay, we have an object that's represented by this arrow right here that can be anything. It could represent a car, it could represent a house, it could represent a person. Today we'll say that it represents Mr. Aiello. Okay, this object right here, this arrow is Mr. Aiello. The top of the arrow is Mr. Aiello's head. Mr. Aiello's head is kind of shiny, which means that there's millions of rays of light that reflect off of Mr. Aiello's shiny head. We want to pick two of them. We could draw 1,000,000 rays, and we would get the exact same attributes or characteristics of the image, but we don't need to draw 1,000,000 rays. 2 rays are enough to tell me what the image is going to look like. The first ray that I want to draw is that ray that reflects off of Mr. Aiello's shiny head to the mirror. Sorry, to the lens, I should say. That ray will refract or bend down here through the focal point of the lens. We know that all rays parallel to the principal axis go through the focal point, right? So this ray is going to refract down through the focal point. Now, I may have mentioned this yesterday, I'm not sure. This is a bit of a simplification, what we did here. It doesn't really bend once down through the focal point. What really happens is that when the light strikes the boundary between the air and the lens, it bends. And then when it strikes the boundary between the lens and the air, it bends again. But the net effect is what we do the first time. So we're not going to worry about actually drawing the proper refraction taking place in there because the end effect is exactly the same. It's a little bit easier to draw it the way we drew it, so let's take advantage of that. The second ray is going to go from the top of Mr. Aiello's shiny head down through the optical center. Where does it go from there? Keeps going straight down. Doesn't really keep going straight down. It really bends twice. But the net effect is the same as if it went straight down. Now, these two rays intersect down here. They come from Mr. Eyeler's shiny head, the object, so they're going to intersect at the image of Mr. Eyeler's shiny head. In other words, this is what our image is going to look like right here, from the principal axis to where the rays intersect. Now, let's look at that image. Let's look at that red image compared to the black object here. This red image is larger, smaller, the same size as this black object. It's larger. This red image is right side up or upside down compared to the object. Upside down. We're going to call that inverted. I don't really care what term you use for that. Some people say inverted, some people say upside down, some people say flipped. It doesn't really matter as long as you recognize what it looks like. And third, this is the tricky one. We talked about this a bit yesterday, but this becomes more clear as we move forward here. We would call this a real image. A real image is an image that can be projected onto a screen. Like the image at a movie theater is being projected onto a screen. The image that you're looking at right now, literally, is being projected onto a screen. Those are real images. When you look in the mirror in the bathroom in the morning, that's a virtual image. You can't, no matter what you do, you can't project the image of you onto the wall behind you. You have to look at the mirror in order to see it, a virtual image. Okay, this is a real image. It could be projected onto a screen. We know that it could be projected onto a screen because it's solid lines that intersect. Now, somebody this morning said, where would we have to put the screen and where would we have to stand in order to see this image projected onto a screen? This is where I'd put my screen. If the image is formed at that spot, I'd have to put my screen right there. If I put my screen right here, I would still see something on the screen, but it would be blurry because the rays aren't converging at that spot. It wouldn't form a good focused image on that green spot. So there's the blue one is where my screen should be in order to see this. Where would I have to stand? Back here. It's like a movie theater, right? When you're sitting watching a movie at a movie theater, where's the screen? In front of you. Where's the projector? Behind you, right? So here's you in the movie theater looking this way at the screen. Here's the projector back here. Here's the image formed upside down right here. Now, you don't watch a movie upside down, right? Nowadays in a movie theater, they actually have two lenses, a two-lens system. So you flip over the image, then you flip it over again, and you magnify it both times, which is why you get such a big image on the screen. That's the idea. It's just that it's not upside down. Okay, let's take a look at another one here. Let's take a look at this one. This time our object is really close to the lens this time. It's like a magnifying glass, right? Okay, I got some print on this page in front of me, but my eyes are getting bad. I can't see it very well. So sometimes I might take a magnifying glass, try to magnify that print. When I do that, I put the magnifying glass nearby the print. In other words, if the focal length of the magnifying glass is 10 centimeters, I want to make sure the print is maybe 5, 6, 7 centimeters from the lens. In other words, I want the object distance, the distance from the print to the lens, to be smaller than the focal length. First ray is going to reflect off of the top of Mr. Eyeler's shiny head, and it's going to go down through the focal point, and then the second ray is going to go down through the optical center. Those don't intersect, do they? If they don't intersect, let's extend them back like this. When I extend them back like this, you find that they do intersect back here. There's my image. This red arrow pointing up is what Mr. Eyeler looks like with this lens. What are the characteristics of that image? Is it larger, smaller, same size? Image compared to the black object. It's larger. Clearly, it's larger. Is it upright or inverted? Does Mr. Eyeler look like he's standing on his head or standing on his feet? On his feet. It's right side up, right? The arrow is pointing upwards. We're going to say upright. Right side up, whatever you want to say that means the same thing. Third one, real or virtual? Yeah, this is virtual. We know that it's virtual because dotted lines intersect. Now, what does that really mean? It means that we cannot project it onto a screen. If you want to see this one, you've got to physically look into the lens to see it. You would be standing over here somewhere, looking into this lens, you would not see this. You would see this. Right? When you look into the mirror in the morning, you don't actually see yourself, because yourself is where you are. What you see is an image of yourself behind the mirror. In this case, what you'd see is an image of Mr. Ello behind where he really is. What kind of lens is this? Concave, right? Or caved in the middle. Concave, caved in the middle. What's the other word for a concave lens? Diverging. Because the rays of light don't converge at a focal point, they diverge away from the focal point. This is our principal axis. This is our optical center. This is F, and this is 2F. This is Mr. Ello again with his shiny head. First ray reflects off of Mr. Ello's head, goes to the lens. Now, it doesn't go down here, because that would be a mirror reflecting it. It doesn't go down here. Rather, it goes up here away from the focal point. Draw it away from the focal point and then extend that ray back towards the focal point like I have right there. The second ray goes right through the optical center, just like it did with the converging lens, I should say. Looks like this. The rays intersect right here. The characteristics of this image, this red image is smaller than the object. It's upright. And this red image is real or virtual? It's virtual. Dotted lines intersect. It's a virtual image. It means if you ever want to see the image formed by a concave lens or a diverging lens, you got to physically look into the lens in order to see it. I can't think of a lot of real applications for diverging lenses. Like most times you don't want to produce an image that's smaller and right set up. Usually you want to magnify something, right? The one situation that I can think of where we use a diverging lens a lot is to correct myopia. Okay, I have myopia. Okay, that means that I cannot see things far away. If I take my glasses off, I can count the number of people in this room, but especially towards the back of the room, I can't tell who you are. That's myopia. I can't see things far away. That means that rays of light that are going through the convex lens or the converging lens that is a part of my eye naturally converge, and they come together and form an image that's in front of my retina. The rays of light keep going and hit my retina, but they're not focused when they hit my retina. So what I want to do is, where they come together, where they focus in front of my retina, I want to move that back a bit. To move that back, I've got to spread the rays apart a little bit, and I use a diverging lens in front of my eye to do that. Now, if I have hyperopia, that means that I can't see close by things. In other words, I need reading glasses. That means the lens of my eye is causing rays of light to converge and focus behind my retina. Those rays still strike my retina, but they're not focused on my retina. So what I got to do is bring that image forward, and to do that, I use a converging lens to cause rays of light to converge a little bit before they hit the lens of my eye. Does that make sense? How many of you guys are wearing contacts right now? Contacts work in a similar yet different principle. Similar in the sense that they refract light in the same optical ways as glasses refract light, except that with contacts, you're not causing light to either spread apart or come together before they strike your eye and correcting before the light hits the lens of your eye. What you're essentially doing is changing the shape of your lens with a contact. And that's why the contact lens can be so much thinner and still have the same effect as regular glasses. It just makes the lens of your eye thicker in the middle or a little bit thinner relative to the edges with the contacts. Does that make sense? Still refracts light. It's still the same index, properties of refraction. It just the mechanics of it end up being a little bit different. The science isn't, but the mechanics are. Good? Okay, yesterday we learned two equations that described all this. The first one we called the thin lens equation. 1 over F is equal to 1 over DO plus 1 over DI. And the second one we called the magnification equation. M is equal to HI over HO equals, this is on your data sheet, but refresh my memory. HI over HO equals, Dylan? Good. That's what I was looking for, the negative DI over DO. It's not HIHO, DI, DO, HIHO, negative DI, DO. And that negative is really important here in order to maintain the sign convention of what we're doing here. Now, if you remember from yesterday, we had kind of two sets of variables here. We had F, DO, and DI. They kind of go together in my table. And then HI, HO, HI, and M kind of go together in my table as well. If you want F, you want DO, and you want DI to be positive, then they have to be real. A real focal point will be a positive F. A real object will be a positive DO, and a real image will be a positive DI. On the other hand, a virtual focal point will be a negative F, a virtual object will be a negative DO, and a virtual image will be a negative DI. When do you get a positive and negative F? When do you get a real and virtual focal point? Well, if it's a converging lens, it's a real focal point, so a positive F. If it's a diverging lens, it's a negative F, negative focal point. When do you get a positive DO? For us in Physics 30, always. You'll never get a negative DO. Negative DO occurs when you have a virtual object, which can happen if you have, I talked earlier about that movie theater system where we have two lenses. You can get a virtual object there. But with the problems that we do, that's never going to happen. So DO is always going to be positive for us. Now, HO, HI, and M, they're not based on real or virtual. They're going to be positive if they're upright. If HO is right side up, it's positive. If the image is right side up, then the HI is positive. If the image is right side up compared to the object, then M is positive. If the object is upside down, if the image is upside down, then HO, HI, M, whoops, are negative values. Remember those sign conventions. There's no way around that. We got to remember those. Okay, if we get a sign wrong, as small as a problem as it might seem to be, you get a question completely wrong. You have no hope of getting it right if you make something positive that's supposed to be negative. We had two questions for homework. I want to do both of these questions. They look almost the same, like almost identical. One difference is that we have a converging lens in the first one and a diverging lens in the second one. We're going to go through both of them. We're going to illustrate how two questions that are virtually identical to one another can produce completely different answers. Question number one says a 12 centimeter tall object. Now, we got to assume that the object is right side up. So we're going to make HO positive 12.0 centimeters. That's the one variable. It's pretty safe to assume that it's right side up if it doesn't specify the object. Okay, we'll just assume that it's right side up, unless it actually specifies that it's upside down. Now, it's in front of a converging lens that has a focal length of 10 centimeters. A converging lens means that we have a positive focal length, because a converging lens causes rays to actually converge at the focal point, which means it's a real focal point, which means it's a positive value. So I'm going to write down F here is positive 10.0. That's the one difference between this question and the next question. The next one, it's negative 10.0. We want to determine the image, we got one more variable here. The object distance is plus 15.0 centimeters. How did I know that the object distance is plus 15? For us, it's always going to be positive, right? Just make it positive. Now we're looking for the image distance, DI. We're also looking for the image height, HI. And we're also looking for the magnification. We're looking for attributes as well, but we'll worry about that after we've solved the math. You only have two equations. Just write down one and try it. Doesn't get you an answer. Write down the other one and try it. I'm going to say, first of all here, I'm going to say 1 over F is equal to 1 over DO plus 1 over DI. 1 over 10 equals 1 over 15 plus 1 over DI. Now, I showed you guys yesterday a little trick on the calculator if you're not good with fractions. I'll show you again. we're going to say 1 over 10, which is just 10x to the minus 1 on your calculator. But I got to take the 1 over 15 over by subtracting. So I'm going to say 1 over 10 minus 1 over 15. 15x to the minus 1. That gives me not the answer. That's 1 over di. So how am I going to find di? Just hit 1 over that number. And we get 30. So di is positive 30 here. The image distance is positive 30, which gives me one of the attributes right now. If the image distance is positive, I know this image is going to be, if the image distance is positive, remember f, do, and di go with, if the image distance is negative, it's going to be virtual. If the image distance is positive, it's going to be real. Remember, f, do, and di, positive means real. Real focal point, real object, real image. This is a real image. We know that because it has a positive di. Okay, let's find something else now. Let's say m is equal to negative di over do. Negative 30 divided by do, which is 15. That gives me negative 2.0. What does that tell us? What does the fact that it's 2 tell us? Forget about the negative for a second, just the number 2, bigger or smaller. If the magnification is bigger than 1, the image is bigger. If the magnification is smaller than the 1, then the image is smaller. So 0.5, it's half the size of the object. 2, it's twice the size of the object. This is a bigger image. It's larger due to the fact that the magnification is 2. And due to the fact that it's a negative magnification, it tells us that the image is inverted, upside down. A negative hi, a negative ho, a negative m refers to right side up, upside down. Negative hi, upside down image. Negative ho, upside down object. Negative m, upside down image. Finally, we want to find the value of hi. Let's say m is equal to hi over ho. Let's rearrange that. We'll say hi is equal to m times ho. That's going to give me negative 2.0 times ho of 12. Gives me negative 24 centimeters. Now, we already established that it was upside down, but this is just more evidence for that. The fact that we get a negative hi. Negative hi doesn't mean it's virtual, and negative hi means it's upside down. But we already knew that from the magnification. Now, you could also determine that it's bigger as a result of this, right? You look at the object height is 12. The image height is 24. Well, that's bigger. It's twice as big. Now, let's look at number 2. My givens are almost identical. HO is plus 12. We're going to say F. F is negative 10 because it's a diverging lens. DO is 15. We're looking for the same variables. So let's just do this the same way. 1 over F is equal to 1 over DO plus 1 over DI. 1 over F is 1 over negative 10. 1 over 15 plus 1 over DI. Is this not going to be the same as the other one? No, it isn't. Isn't it going to just be opposite, negative 30? No, it isn't. Let's pull out the calculator again. Let's say negative 10, 1 over negative 10, subtract 1 over 15. Let's flip that over, and I get negative 6. I get a negative DI. Remember, F, DO, and DI are all positive, negative, are based on real or virtual. Negative DI means, negative means virtual, right? For F, DO, and DI, negative means virtual. This is a virtual image because DI is negative. Careful with this. Negative DI, negative 6. Does that make sense? DO is 15. I think that gives me 0.40. 0.4 tells me that the image is smaller, yes, because it's only 40% the height that it was. And the positive M tells me that the image is right side up or upside down. Right side up. Remember, HI, HO, and M refer to right side up or upside down. F, DO, and DI refer to real or virtual. So we're going to say this is smaller, and we're going to say that it's upright. And we want to find HI now. HI is equal to M times HO. It's 0.40 times the object height of 12. Gives me 4.8 centimeters. I don't know if you guys caught this or not, but this actually carries through the whole way. There's a pattern formed here with these signs. If you have a positive DI, in other words, if you have a real image is always upside down. And a virtual image is always right side up. So if you have a positive DI, you must have a negative HI. If you have a negative DI, you have to have a positive HI. Does that make sense? You don't have to memorize that, because in the end, you could always go back to your ray diagrams, right? But sometimes it's useful to remember little things like that to kind of tell you if you've got a right answer or a wrong answer. All right, those are good for you. I'm going to ask you to do now for the rest of class questions 3 and 4. These are, I would suggest, a little bit trickier than questions 1 and 2. Give them a try, see what you can do with them. I think you guys can swing it here.